Okay, good day to everyone. Today we are going to discuss part 6 of module 2 of the subject CE3151. So I'll be discussing inverse of matrices. So the inverse of a matrix is denoted by the name of the matrix raised to negative 1 and is sometimes referred to as the reciprocal matrix. The inverse matrix is only applicable for non-singular matrices, meaning if our matrix will have a determinant equal to 0, which defines it as a singular matrix, then that matrix is considered as a matrix that is not invertible. So to understand inverse matrices, we compare now numbers with matrix. So for numbers, they will have reciprocals, thus matrices will have what we call the inverses. So for numbers, if we have 2, then its reciprocal is 1 over 2. Therefore, 1 over 2 can be written simply as 2 raised to negative 1. While for matrices, matrix A is equal now to A raised to negative 1. Thus, A raised to negative 1 cannot be written as 1 over A, since matrices are not to be divided. So, in sense, the inverse of a matrix would look like the division for simple numbers. So if a number is multiplied to its reciprocal, we have 2 times 1 over 2, it will give us a value of 1. Likewise, for a matrix, when it is multiplied to its reciprocal or to its inverse, we have matrix A multiplied to its inverse will result now to an identity matrix, wherein the identity matrix is like the number 1 in context of matrix. This means now that an inverse of a matrix can be defined simply as a matrix which when multiplied to its inverse will result to its identity. Take note that for singular matrices, they cannot be inverted since the determinant is equal to 0. So for a 2 by 2 matrix, the inverse now of this matrix can be written as 1 over AD minus BC multiplied to the matrix D, negative B, negative CN, A. So take note that AD minus BC is the determinant of the matrix or the original matrix, and the matrix here is equivalent to the adjoint of the original matrix. Therefore, the inverse of matrix A can now be computed as the adjoint of the matrix divided by the determinant of the matrix. This equation can be applied to any square matrix. So, this equation can be applied to a 3 by 3 matrix, a 4 by 4, or a 5 by 5 matrix. So, to understand inverses, let us solve problem number 22. So, evaluate the given matrices if they are invertible. So, we have matrix K, which is a 3 by 3 matrix. So, to determine if the matrix K is invertible, we solve first for our determinants. So, for our determinants, that will now be 2 times 2 times 2 plus 3 times 3 times 2 plus 2 times 1 times 3. And that is equal to 32. So minus 2 times 2 times 2 plus 3 times 3 times 2 plus 1 times 3 times 2. which is also equal to 32. So therefore, the determinant of k now is equivalent to 0. So when the determinant is equal to 0, this is now a singular matrix. Therefore, the matrix K cannot be inverted. So we have another matrix S, which is also a 3 by 3 matrix. So to determine if it's invertible, let us solve for its determinant. So we have 1 times 5 times 1 plus 2 times 4 times 3 plus 3 times 4 times 2. So that is 53. So minus 3 times 5 times 3 plus 2 times 4 times 1 plus 1 times 4 times 2. And that is equal to 61. So 53 minus 61 is now equivalent to negative 8. So the determinant is not equal to 0. Therefore, the matrix S can be inverted. So we have another matrix P, which is also a 3 by 3 matrix. So same procedure, we determine first your determinant. So that will now be 1 times 1 times 1 plus 0 times 0 times 1 plus 1 times 0 times 0, which is now equal to 1. So that's minus 1 times 1 times 1 plus 0 times 0 times 1 plus 1 times 0 times 0. And that will give us equal to 1. So 1 minus 1, the determinant of matrix P is equal to 0. Therefore, matrix P is not invertible. So let's solve another example, number 23. Determine the inverse matrix of matrix Q in problem number. So from problem 18, we have matrix Q, which is a 3 by 3 matrix. And from 18, we were able to determine its determinant, which is equal to 22. Since the determinant is not equal to 0, therefore matrix Q can be inverted. And to get now the inverse of matrix Q, we have identified that the inverse of a matrix is simply equal to the adjoint of the matrix divided by the determinant of the matrix. So we have identified already the determinant of Q. So what we need now is the adjoint of matrix Q. And the adjoint is simply defined as the cofactor or the transpose of the cofactor of the matrix. So what we will do is to identify first our cofactor. So for element 1, 1, that will now be positive 4 times 6 minus 5 times 0. So that's equal to positive 24. So next we have element 1, 2. So our element now will be negative 0 times 6 minus 1 times 5. So we'll have negative 5 times negative. Next we have element 1, 3. So we'll have positive 0 times 0 minus 1 times 4. So that will be negative 4. So next we have element 2, 1. So we'll have negative 2 times 6 minus 0 times 3. So we'll now have negative 12. Next we have 2, 2. So that will now be positive 1 times 6 minus 1 times 3. So that is equal to positive 3. And then we have 2, 3. So we have negative 1 times 0 minus 1 times 2. So that is now equal to negative 2. So next we have 3, 1. So we'll have now positive 2 times 5 minus 4 times 12, or that will give us positive negative 2. Next, we have 3, 2. So that will now be equivalent to negative 2 times 5 minus 4 times, that is 1 times 5 minus 0. So that is equal to negative 5. And lastly, we have 4, 3, 3. So that will now be equivalent to positive 1 times 4 minus 0, or that is now equal to positive 4. So get now your transpose. We'll be able to solve for your adjugate of the matrix Q. So we already have your determinant. You also have your adjoint. So we apply now your inverse. So the inverse now will simply be 1 over 22, which is your determinant. This one is our adjoint. So just simply distribute your determinant, since it's a scalar value, to all of the elements. Then we have now the inverse of Q is equal now to this matrix. Okay, so 24. So pareho lahat ng numerator, nagkaroon lang ng denominator. So if we're going to multiply this matrix to your original matrix, your answer should be an identity matrix, meaning all the diagonal is equal to 1. So let's solve problem 24. Determine the inverse of the matrix H, which is a 3 by 3 matrix given the following elements. So we solve first for your determinants. So the determinants now will be 1 times 1 times 1, 2 times 3 times 3, 3 times 2 times 2. So subtract now 3 times 1 times 3 plus 2 times 3 times 1 plus 1 times 2 times 2. So simplifying this now, our determinant for matrix H is positive 12. So it is not equal to 0, therefore matrix H is a matrix that can be inverted. So since it can be inverted, we can now solve for your adjoint. But before that, we have to identify first your cofactor. So for our cofactors, we know that for our elements, it will have a sign convention of positive, negative, positive, positive, negative, positive, negative, positive, negative, positive. So let's solve for the first row first. So we have 4 element 1, 1. So that will be 1 times 1 minus 2 times 3. That is negative 5. Next, we have element 2. So that is 2 times 1 minus 3 times 3. So that is negative 7. Next, we have 1, 3. So that is 2 times 2 minus 3. that is equal to positive 1. So second column, we have 2, 1. So we'll have 2 times 1 minus 2 times 3. So that is equal to negative 4. Next, 2, 2. That is equal to 1 times 1 minus 3 times 3. So that's negative 8. And then we have element 2, 3. That is now 1 times 2 minus 3 times 2. So that's negative 4. So for the last row, so 3, 1, it's 2 times 3 minus 3, that is positive 3, 3, 2, that is now 1 times 3 minus 2 times 3, that's negative 3, plus our last element, that is 1 times 1 minus 2 times 2, that is now negative 3. So from our cofactor matrix, we can now solve for our adjoint matrix. So for our adjoint, just transpose. So this one becomes negative 5, positive 4, positive 3. So for the second column, this now becomes our second row, that is positive 7, negative 8, positive 3. For our last column, that will now be our last row, positive 1, positive 4, minus 3. Okay, so from there, we can now compute for our inverse, which is equal to 1 over your determinant, 12, multiply that to negative 5, 7, 1, 4, negative 8, positive 4, positive 3, positive 3, negative 3. So we'll now arrive at negative 5 over 12, 7 over 12, 1 over 12, 4 over 12, negative 8 over 12, 4 over 12, 3 over 12, 3 over 12, negative 3 over 12. So this is our final answer. So for number 25, determine the inverse matrix T, which is a 4 by 4 matrix. So I have learned already how to compute for the determinant of a 4 by 4 matrix by Laplace method or by pivotal element method. So using either of the two methods, we'll arrive at the determinant of T, which is equal to negative 16. So it's not equal to 0, therefore matrix T can be inverted. So also, we have learned already how to get the cofactor of a 4 by 4 matrix and as well as the adjoint of a 4 by 4 matrix. So from there, the adjoint matrix of T is given by this matrix. So for our inverse, we just simply multiply the adjoint to 1 over negative 16. Thus, simplifying now, this equation will now arrive at final matrix of the inverse, which is having a magnitude of 1/4 for every element.